Buddy, I, Ruchi Singh and Komal Babar of Tech University is going to present a project on low power correlation for IEEE 802.16 ofdm synchronization. The basic approach for that project is we are designing a correlator which will be helpful in low power devices with the help of synchronization in ofdm. Project revolves around three topics. First one, ofdm, IEEE 802.16 and the correlation. For the ofdm, it is basically method to encode the digital data on multiple carrier frequencies for both wired and wireless. In ofdm, what we are going to do, we are going to use a large number of closely spaced orthogonal subcarriers which are used to carry the data on several parallel data stream or channel. Each subcarrier is modulated with a conventional modulation scheme, example quadrature amplitude modulation. The basic advantage of the ofdm technique is ability to cope up with the several challenge conditions without complex equalization filter. In IEEE 802.16, it is officially called as wireless MAN and commercially as WiMAX. It standardizes the functions associated with WLL. WiMAX is worldwide interpolability for microwave access. The network architecture consists of subscriber stations, base station and mobile station. Project is correlation. The correlation between the two random variables at two different points is a function of the temporal distance between the 2 points. If the correlation function between the random variables represents the same quantity measured at two different points, then it is an autocorrelation. And the cross correlation function will be the correlation function of two different random variables. Correlation indicates the dependency as a function of the distance of time. Autocorrelation is measured with the two signals coming from the same source, while cross correlation is measured with the two signals coming from the different sources. We are going to compare one multiplier-less circuit with the multiplier-based circuit using the cross-correlation technique for the timing synchronization. The existing approach is a multiplier-based circuit DSP block standard, but it consumes huge number of DSP blocks, hence not suitable for the low-power devices. Hence, we propose a multiplier-less circuit which will actually eliminate the need of multiplication operator, and it will replace it with the shift and add operations. While comparing it to the DSP-48 even slice-based design to the multiplier correlation in the terms of resource utilization and power consumption, ofdm timing synchronization is evaluated. Results shows that it produces the same accurate timing synchronization. Multiplier-less circuit consumes less powers over the slice-based design and can be used where slice resources are insufficient, such as low-power devices. Architecture basically consists of a multiplier-less circuit which will use the shift and add operations instead of the multiplication operator. In the real-time application, digital filters are implemented in hardware. In hardware realization, to reduce the cost, it is desirable to minimize the number of general multiplication, and the multiplication by a fixed power of 2 is easy to implement. Hence, it requires only addition and the power of 2 multiplication for implementation. 2 power for this, we can use the shift and add operations. In the multiplier-less correlator, it represents the coefficients and round them in the form of some power of 2. Hence, shift and add operation is required for the multiplier-less circuit. Autocorrelation is used because of the low cost. FPGA with the parallel architecture is used for the ofdm transceiver. Timing synchronization is obtained by the double autocorrelation based on the short training symbols that allows reduction in hardware cost on FPGA. But for FPGA, the cross correlation is better than the autocorrelation but comes at hardware cost. So what we are proposing is we are using the cross correlation technique with the help of multiplier-less circuit to avoid the reduction in the hardware and the cost. The basic block diagram, what we are going to do in this project, it basically comprises of a transmitter, receiver, and in between it has channel. When the wave propagates through the channel, it gets disturbed by various other sources present out there in the channel. Hence, the orthogonality of the transmitted symbol gets lost. Therefore, we are going to overcome this the orthogonality loss in the channel itself. Propagation of the signals through the channel, the signals get disturbed by various other sources. Therefore, when the signals arrives at the receiver, it has lost its orthogonality. Hence, the need for synchronization comes into picture. Is needed because of the two factors, that is symbol time offset and carrier frequency offset. In the symbol time offset, the transmitter and receiver do not have a common time reference. Receivers needs to find the symbol boundaries to avoid ISI and ICI. In the carrier frequency offset, the carrier frequency phase of the transmitter local oscillator and the receiver local oscillator cannot be off by some ppm, resulting in a frequency difference between the transmitter and the receiver carrier frequencies, which introduces an additional term of e power j2 pi del fc by fgn in the receiver. Hence, we need to compensate for this frequency difference. So, when del fc does not equal to 0, where del fc is the basic frequency difference between the two carriers, each subcarriers of the multi-carrier symbol ends upon a position shifted by the del fc compared to the transmitter. Hence, the orthogonality get lost. So, because of this impact, the synchronization is needed. That's why we are going to synchronize everything in the channel itself. Carrier symbol ends upon a frequency position that is shifted by del fc hertz compared to the transmitter. Therefore, the orthogonality of the subcarrier is gone, so the need for synchronization arises. This disadvantage, cyclic prefix methods is used. In cyclic prefix method, it determines the frequency offset and symbol time but do not determine the start of frame by themselves. In the cyclic method, it refers to the prefixing of a symbol with the repetition at the end. Although the receiver is typically configured to discard the cyclic prefix samples, it serves two purposes. First one, as a guard interval, it will eliminate the ISI from the previous channel. Second one, as the repetition at the end of symbol, it allows the linear convolution of the frequency selective multipath channel to be modeled as circular convolution. The basic advantages in OFDM is that it is used to combat the multipath by making the channel simulation easy. But in the basic disadvantage of cyclic prefix method is that it cannot detect the plateau with it. It cannot detect the plateau within that symbol unless frames arises. Hence, the need for preamble arises. So, what happens in the preamble? It will consist of two cyclic prefix symbols. The first one is followed by 464 bit and the second one is followed by the 128 bits, two 128 bits. The 464 bit symbol is called a short training symbol and the two 128 bit symbol is called the long training symbol. Earlier in this technique, the 464 bit training symbols is used for the autocorrelation. What happens over there? It will get autocorrelated and it will arise a plateau over there. So we are going to compare that plateau with the threshold function. If the threshold lies within the plateau, then we can actively achieve the autocorrelation. But the basic disadvantages over there was, we cannot, what if the threshold is greater than the cross correlation, or cross correlation is greater than the threshold, then we cannot detect the trailing symbols with the help of autocorrelation function. So the need for cross correlation arises over here, and the long trailing symbol is used to determine the multipath fading effect while propagating through the of the transmitter. Here, to send the data bits using OFDM, the first thing is the number of subcarriers that are required to send the data. Assume there are n carriers and all are orthogonal. Second design parameter will be the modulation format we use to wish. The data D has to be first converted from serial stream to the parallel stream depending upon the number of subcarriers. Since there are n subcarriers, then we name them from 0 to n minus 1. Now, serial to parallel converter takes the serial stream of input bits and outputs n parallel bits indexed from 0 to n minus 1. These parallel streams are individually converted into the required digital modulation technique. We are using QAM. The conversion of parallel data into the digitally modulated data is usually achieved by the constellation mapper, which is essential in the lookup table. Once the data is modulated, they are needed to be superimposed on the required orthogonal subcarriers of the transmission. They are achieved by n parallel sinusoidal oscillator tuned to n orthogonal frequencies. This can be done by using IIFT operations, which will eliminate the need of individual multiplication operator, which will orthogonal the signal, which is the harmonic of each other. Hence, these are at last what happens. They are the strings which are parallelly entered is serially converted, and the data is transmitted through the channel to the receiver section. After propagating through the channel, it will go to the correlator. Correlator are used to retain back the original signals that was transmitted. Here we are going to compare the two types of correlator, one with the multiplier based correlator and the other one will be the multiplier less correlator. Of the multiplier based correlator, which consists of the multiplication operator, what happens, it will assemble and add the 64 preamble signals. We are using 64 different preamble signals, which will be multiplied, added and decoded together through the pipeline structure. This is the transport direct form of multiplier based correlator. It also uses the data part to be configured for various input combination and register stage. A 3-stage pipeline offers the maximum performance. Hence, in this approach, only 3-stage pipelining stage has been performed. In non-pipeline slices, the transport direct form of 64 coefficient PR corresponding to the 64 complex conjugate values of the samples in the preamble. Relator represents coefficients and round them in the form of some power of 2. Hence, shift and add operations is required instead of multiplication. Since the P, R of n values are constant after synthesis, the design in the multiplexers is optimized as a hardwired logic and the preamble cannot be changed. To support different OFDM preamble, the PR of n could be stored in a register and a real multiplexer uses instead of hardwired logic. This results in increased resource utilization but provided more flexible solution. Consists of the receiver section where the data is entered from serial to parallel and here the cyclic prefix what we have added in the transmitter section will get eliminated. After that, from the FFT operation, fast Fourier transform operation, the orthogonal signals are retrieved back. In the modulation technique, what we have modulated, the decoder of the constellation will demodulate the signals which is fed to the parallel to the serial converter, which will output the data into the serial form. Consists of the 3 parts, its transmitter, channel and the receiver. The TX modem represents the transmitter section, TX RX represents the channel and the RX modem represents the receiver section. Result what we have done in our project, it consists of the inputs are clock, reset, transmitting serial and receiving serial. The transmitting serial initially will assign 1111 to each and every one, that is clock, reset, transmitter and receiver. It will indicate that while it is 1 we have reset everything, but after making it to 0, the transmitter will start transmitting and the receiver will start receiving. The IIN input will represent the FFT and IIFT operations over there. Thank you very much. This is Komal Babar signing off from our project. Thank you.